So let's start. So I talk about application of medical learning, and this is a two-dimensional Radon tomography application. And so let's take a look at what it is. So the main reference is this paper, two-dimensional tomography from noisy projections taken at non-random directions. And you can find some papers cited inside which used other methods and so on. And this paper is kind of old, 2013, but I still consider quite a challenging problem. There are some following up works. And there are some basic textbooks that I found very useful. Like this one is what I grew up with, so you can maybe take a look if needed. So let's have a very quick discussion of the setup. So what is a shape-loaded phantom? This is a shape-loaded phantom, which looks like this, which you can view it as a function defined on R2, and this is actually an object of interest, like here, put in the center of XY plane. Okay, so it's a two-dimensional image. So let's consider theta, which is in S1. We view it as a projection direction. Okay, and this is how it is projected, and this is a projection direction theta. And so just be careful. Sometimes we just abuse the notation. Theta in S1 just means it's an angle, but sometimes we use theta and put it inside cosine. Then this is really an angle, and this is a direction. So technically, well, whatever, that's the same. But anyways, this is a theta in S1, and this is a projection direction, which is a vector representing the direction. Okay, so this dashed line is actually the line perpendicular to mu theta. So sometimes we just denote it as a v theta perpendicular, and we can shift it here so that we can better visualize the information, what we want to demonstrate. Okay, so now this is what we have. We have theta projection direction, and that is the line equal to v theta. And we just shift this line here and consider one point, because x0 then is the intersection of this line, this projection angle, and this dash x0. So what is X-ray transform? X-ray transform is defined in the following way. It is r psi theta. Theta is the projection direction. X0 is this point. And what we do is we will consider integration of everything of the function psi over this curve. Okay, so we just integrate everything when the function is restricted on this point. Okay, so that is a kind of easy to understand, but certainly you may pay attention to the meaning of psi. What does it mean by evaluating one point of a function? For example, if psi is just L2, what does it mean? But let's forget about this technology and assume everything is good. Now you can consider all the projections with the projection direction theta, but you can consider different points in the different projection lines. Okay, so you get psi, r psi theta, which projects from every point over r. This is r, this r, okay, and you get one value. And this is the function you get after projection. And this is actually a function defined on a particular line. Okay, so that is our X-ray transform. And the usual goal is we want to explore or understand psi, this function, from the set of data that is from all the projected direction. And you know what theta is. And this set of data is called sinogram. Sino, S-I-N-O, not so, sino, S-I-N-O, sinogram. And this is how it looks like, sinogram. This is the projection direction. This is on the projected direction, on the perpendicular projection direction. So you can see it's kind of beautiful waves, isn't it? Okay, so a very quick recall, although we will not go into details, about how to reconstruct the original signal side that we have interest from the sinogram via inverse X-ray transform. It's called X-ray transform, inverse X-ray transform, or inverse Radon transform. You can apply it to sinogram to recover psi. And the key is you need all projections and their associated projection angles. Otherwise, you cannot do the recovery. And there are several techniques, algorithms to implement it numerically, but we will not detail it in this lecture. So the most common one is called filter back projection algorithm. The key idea is a projection plus projection two phases. This is actually a huge topic, and you can go to a textbook if you have interest, if you need it. And we'll skip detail here, and then maybe we'll discuss it in a future lecture if needed. So now, let's have a quick recall of the relationship between X-ray transform and the Radon transform. So, in the general n-dimensional space, right now we are talking about R2, but in general, X-ray transform of a function f on the n-dimensional space is defined as an integrating f over all trinites parameterized by theta. So that is how it looks like. Easy to understand. In Rn, the Radon transform is kind of you can view it as a dual of the X-ray transform. That is, it is defined as integrating f over the set of all hyperplanes. And this is the definition. Because C is a hyperplane, and you just do integration. And alternatively, you can write Rf C as theta S, because we use the fact that C can be written as all the set X such that X inner product theta is S for some S on a sphere. That's a very basic property, and you can write it in this way, which sometimes is easier to understand. X inner product theta is S, and that is S and theta. Okay, so in Rn, the generalized Radon transform of a function can be further defined or can be further generalized. It is defined as integrating over k dimension affine subspaces, sigma k. So that is what you can easily define and easily imagine. And then in this setup, you see the X-ray transform is just a spatial generalized Radon transform with k is 1. This is, in this case, kind of X-ray transform is a spatial Radon transform, and when you consider two-dimensional space, actually the hyperspace is one-dimensional, so X-ray transform is the same as Radon transform. So sometimes we just, in two-dimensional space, we don't distinguish in between Radon transform, X-ray transform, and there are many interesting properties of Fourier transform, like size Fourier transform, Fourier series, and so on, that you can find in the textbook, but we will not go there. So now, after have this 2 minutes quick review of the relationship or some basic knowledge, let's start to ask the question: what are we doing? Because we are working with computer, right? So we cannot really work with something L2 or continuous space or something. We need to have some assumptions. So what we have is, this is S1. You choose a projection direction theta, and you apply X-ray transform. Now you get the R side of S1, which is this circle, kind of this shape. And then every point, this point is R side of theta. This is this theta, this point. And in general, you can view it as in the L2 space. So our assumption is, suppose I give you psi, which is an L2 function, is completely supported. Then theta from this point to that point actually is a continuous map from S1 to L2R. And you can easily check this assumption holds in many simple general functions. And now you assume C, if you denote this as C, this guy is C. This guy is compact, continuous, and closed in L2. Then everything is good. That is continuous setup. And how to do a discretization? So we will assume that after the projection, that is what you have, you do the discretization, and the discretization is denoted as dp, which is defined for any function I, it's a continuous function, take the discretization operator dp in this way. That is, you just sample p points. P distinguished points, and usually it's uniform points. And you denote the discretized point in Rp, so that you map from CR to Rp. Okay, and that is how the signal looks like at different location, different points, and so on. And certainly we cannot say, oh, because P, you cannot say, oh, P is very, very small. Suppose P is very, very small, like 1. Then obviously you cannot get anything like a circle, right? Because everything will be reduced to just a discrete point on the line. So you need P to be big enough, and big enough so that we assume that dP of C is homeomorphic to S1. So that the data point, those images as data points are actually sampled or located on a one-dimensional manifold that is at least homeomorphic to S1. That is our ultimate goal. And then, once we get to discretization, we can describe our sampling assumption. So we will sample n points from S1, IID, uniformly. And we assume uniformly right now, and we'll discuss why we need uniformly sampling later. But no matter what, it is uniform here, but because of the Radon transform and discretization, this is a nonlinear operator. What you get will be a non-uniform sampling on the right-hand side manifold. So in the end, you get n IID samples at this discretized one-dimensional manifold, and you denote xi as the dpr psi of theta I. Okay, so in the end, you get x1 up to xn are non-uniformly distributed points on this one-dimensional manifold. So that is the sampling assumption. Under this sampling assumption, what do we want? We want to ask the following question. Suppose those points are given, but I do not give you the projection direction. That is, you only have the point, but you don't know where the points are. Okay? Then please recover psi. And if you remember before we mentioned, if you want to apply inverse X-ray transform to recover psi, then you need to know not just the projected images, but you also need to know the associated projection directions. But right now, I remove the projection direction information and ask if you can recover psi. That will be the challenge. Turns out, this problem can be relatively easily resolved. Why? Because suppose we get all these projection images, and suppose we can recover the angle on S1, suppose we can, then problem solved, right? Because then we can just apply inverse X-ray transform. But the question is, how can we get the angle recovered? Now, we'll discuss two different setups. First, when there is no noise. But as you remember, the title of the paper, or the work, or the challenge is when the data is noisy. But let's start with the noise-free case and see how far we can go, or what will be the properties we can obtain. And then we will continue when the data is noisy. So when the data is clean, we will apply diffusion map. Why? Because diffusion map, based on the spectral embedding theorem we discussed, is capable of allowing us to recover the underlying manifold parametrization. And the underlying manifold have been traced within S1. So by applying diffusion map, actually you can recover everything, the underlying S1 space. Why? Because if you take a look at d theta inverse w theta, and this theta is alpha normalization with alpha 1 case, and you get all the eigenvectors and eigenvalues. Then the eigenvector, in particular top one, will be very close or spectrally converges to the sine of 2 pi L of x. And the second one will be the cosine, where L is the normalized arc length function. And this is the property we discussed before when we discussed diffusion map. Then you just estimate the ordering by ordering of the phases. That is, you know it's sine, this is cosine, so you just consider sine 1, sine 2, division, and find the arctangent. And once you find arctangent, you get the theta estimation. And that will be our estimated desired projection direction. The only difference, or the only kind of thing that we cannot recover, is the fact that the eigenvectors is actually free up to rotation and the reflection. Okay, so this is actually the rotation, and this is just O2. Okay, and so what you get will be the recovered angle freed up to rotation and O2. Not just rotation, but O2. Because you also have free. So this is an example. The real projection angle is the red one, but you see that the recovered projection angle by diffusion map is actually in this direction, and there is a shift. So this is SO2 freedom, and you get this direction, that is the O2 freedom, the reflection freedom. So it should just say O2, not location and O2. I should say just O2. Okay, just remove this one, only O2. Okay, very good. So you can see some comparisons with other embeddings. For example, if you don't use alpha is 1, you use alpha is 0, then you get the non-uniform sampling comes into play. But if your alpha is 1, then the non-uniformity disappears, and you get S1 band. And that is a LLE, which we discussed in the other lectures. Local linear embedding, you can see with big C, with good C, with small c, you can get a lot of different results. So, well, you can play with local linear embedding, which can also give you something good if you choose the regularizer property. But we will not continue with LLE. Okay, and then why do we make an assumption of non-uniform sampling? What about if the sampling is non-uniform in S1? Okay, the problem is if it is non-uniform sampling, then we can still recover the ordering, but we cannot get accurate direction estimation. Why not? Because you lose the information, and you do not have extra structure, geometric structure, that you can utilize. This is a very concrete example. For example, you consider G function, which is from RP1 to RP1. RP1 is the set of all directions in S1, in R2, all direction in R2. And you say, hey, let's consider another function H, which compactly supported. And you can easily request this guy, H, to satisfy this condition. That is, you have its Fourier transform is written as R ei theta, but I will request this R ei theta to be related to G of ei theta, of the function that we have interest. And clearly, if you just focus on those endpoints, then H hat and F hat agree on the central lines, all the central lines. Although, well, then because of different distributions, then you have different angles. But you cannot really get X-ray transform or inverse X-ray transform, done, because you cannot recover, get the true information back. So this is how it looks like. And so it tells you that in a two-dimensional space, in this case, sorry, uniform sampling is important because we can only recover order. And when you go to the three-dimensional space, then you have extra structure that you can leverage so that it's possible to handle non-uniform sampling. But we will not go there But we may go there in the future when needed. Okay, but this is a very, very important topic here because we can only recover ordering. And so, if it is uniform sampling, then we can still get everything almost back. But if it's non-uniform sampling, at least we are able to estimate the non-uniform sampling. Otherwise, we are screwed because we only get the order back. And this is a counterexample that you can easily construct. And what happens when noise exists? Well, then the problem becomes very challenging. Right now, you have noisy data, and also theta I is unknown. And you want to use the noisy data and ask if we can recover the projection angle. Suppose we can, then we can still apply inverse X-ray transform to recover the phantom. However, is it really that possible? Well, the second step, let's see. Suppose we do have the projection direction. Can we still get the phantom back from noisy data? Yes, we can. For example, SNR is 0 dB, minus dB, even minus 10 dB, you can still see quite a lot of structure of the phantom, isn't it? So suppose we can get a projection direction back, everything seems to be good. But the problem is, sorry, diffusion map fails when noise is that big. That is the projection direction you can recover. A lot of confusion appears so that everything you get is like garbage. So we need to do something. We need to do something. And the best idea we have right now, and that will be the focus of the next lecture, will be denoise. If we can denoise the signal, noisy signal, and get the red one is the denoised signal, the blue one is the underlying ground truth. Suppose we can achieve this red signal, then somehow we may be able to recover as much as possible, recover the phantom, and so on. So that will be the next lecture. The very last slide is why do we care? And because this is a simplified version of cryo-EM, and we have discussed cryo-EM in one of the previous lectures, so I will skip it. But it is a very interesting problem.